Imagine the universe not as we see it today, filled with galaxies, stars, planets, and the vast structures we take for granted, but as it appeared more than 13 billion years ago. Picture a cosmos still young, only a few 100 million years removed from its explosive birth in the Big Bang. It was a place without planets and without the familiar constellations we know, a place where the very first lights were only beginning to flicker into existence. The universe was in a state of quiet suspense, like a stage with its curtains drawn back, waiting for the actors to appear. And then, with the arrival of the James Webb Space Telescope, an instrument designed to peer deeper into cosmic time than any device humans have ever created, those curtains were pulled open far wider than anyone expected. The story begins with a sense of curiosity that drove astronomers to build this extraordinary telescope. Webb was crafted to see the first stars and galaxies, to push our vision back to the dawn of creation itself. For decades, scientists dreamed of witnessing the earliest chapters of the universe's story, but the tools available were simply not powerful enough. The Hubble Space Telescope had provided tantalizing glimpses, revealing some early galaxies, but even Hubble's vision blurred before reaching the true cosmic beginning. Webb was built to change that. Its mirrors, instruments, and infrared vision would allow humanity to look so far back that the light from ancient stars would be stretched by billions of years of cosmic expansion. That red-shifted glow could finally be interpreted with clarity. When the first images and data arrived from Webb, astronomers around the world watched with a mixture of awe and disbelief. Instead of a few faint smudges barely distinguishable from the cosmic background, Webb delivered sharp, vibrant portraits of galaxies existing only a few 100 million years after the universe began. These galaxies appeared surprisingly bright, surprisingly massive, and surprisingly mature. The sense of astonishment spread quickly, because these early galaxies seemed to violate the timelines established by decades of theoretical modeling. According to those models, it should have taken far longer for the universe to craft such luminous structures. Yet there they were, glowing in Webb's vision like cosmic lanterns shining through the fog of time. As scientists examined the new data, they noticed something even more remarkable. Scattered among the galaxies were a handful of point-like objects, tiny and bright, more compact than galaxies, but more luminous than any star of their age should have been. Some of these objects were not resolved as galaxies at all. Webb's instruments are extremely sensitive to size and extension, so if an object looks like a point of light, one possibility is that it is a star. But these were not ordinary stars. They were too bright, too large, too anomalous for the early universe. These sources were cataloged with names that sound technical and cryptic, like JD's GS Z14O and JD's GS Z13O. But behind those cryptic names lay profound questions. What were these things? How could they shine so intensely so early in cosmic history? The surprise deepened when astronomers analyzed their light. Webb does not just take pictures, it also spreads light into spectra, allowing scientists to measure the chemical fingerprints embedded within each beam of starlight. Spectra tell us what an object is made of, how fast it is moving, how old it might be, and what processes are occurring within it. As researchers studied the spectra of these unusual bright sources, they found features that did not match ordinary stars or typical galaxies of that epoch. There were hints of signatures consistent with something far stranger, something that had only been theorized but never observed. And this is where the story takes its first dramatic turn. Decades ago, some astrophysicists proposed the existence of a very unusual kind of object, a dark star. Not a star made of darkness or shadow, but a star powered by dark matter. Dark matter is the invisible substance that makes up most of the universe's mass. We cannot see it directly. It does not reflect or emit light. We only know it exists because its gravitational pull influences galaxies and cosmic structures. But in the early universe, when dark matter was denser and more concentrated, it was possible that dark matter particles collided and annihilated each other. If those annihilations released energy, and if that energy occurred inside a forming star, the consequences would be extraordinary. A dark star-powered star could grow far larger and brighter than any normal star. Its fuel source would not be the fusion of hydrogen, but the invisible interactions of dark matter itself. This idea was bold, creative, and profoundly speculative. For years, it lingered on the edges of astrophysical theory, intriguing but unproven. But with Webb's data in hand, astronomers realized that some of the strange luminous sources might fit the profile of these hypothetical dark stars. The mere possibility electrified the scientific community. If even one dark star existed, it would change our understanding of the universe's earliest moments. It would mean that dark matter, usually treated as silent and passive, played an active role in shaping the cosmos. And it would hint at new physics far beyond what we currently know. The sense of surprise grew into something larger than curiosity. It grew into a recognition that the universe might be far more imaginative than our best theories predicted. These bright, point-like objects were not just anomalies. They were clues, breadcrumbs leading into a deeper mystery. The early universe might not have been a calm, predictable environment where simple stars ignited and galaxies slowly took form. Instead, it might have been a dynamic arena where exotic processes unfolded, where enormous luminous bodies powered by invisible particles shone across vast distances, and where the seeds of supermassive black holes were planted much earlier than expected. As scientists probed deeper, they began to appreciate the profound implications of what they might be witnessing. The early universe is often described as the cosmic dawn, the moment when the first true lights broke through the long night that followed the Big Bang. If dark stars existed at that dawn, they would redefine the metaphor entirely. They would not just be the first lights, they would be something more like cosmic beacons, shining with an energy source so unusual that it challenges our most fundamental assumptions about matter and energy. Consider for a moment how strange and wondrous this possibility is. A dark star would be enormous, spanning thousands or even millions times the radius of our Sun. Its surface would be surprisingly cool compared to typical stars, because its luminosity would not come from the intense heat of nuclear fusion. Instead, deep within its core, dark matter particles would collide invisibly, releasing heat that inflated the star to enormous dimensions. From afar, such a star would appear bright, almost like a cosmic lighthouse. But it would not behave like a normal star. It would grow and swell in the early universe, drawing in gas and dark matter alike. In time, it could reach a mass so great that when its dark matter power source eventually faded, the star would collapse under its own weight, forming a black hole far larger than anything produced by normal stellar evolution. This collapsing dark star could then become the seed of a supermassive black hole, the kind of object that astronomers have detected shining as brilliant quasars in the early universe. Such quasars have long puzzled scientists because it seemed impossible for black holes to grow so massive so quickly. But a dark star collapsing into a black hole would provide an elegant solution. Instead of growing slowly from the collapse of ordinary stars, these black holes could begin their existence already supermassive, making their later growth far easier to explain. As Webb's data continued to stream in, the scientific community found itself grappling with this possibility. The early universe was no longer a settled story. It was a frontier once more, full of mysteries and unexpected discoveries. The very instruments designed to deepen our understanding had instead revealed that much of what we thought we knew might be incomplete. The universe surprised us, as it so often does, by being far more complex and imaginative than the theories we built to describe it. This is the mystery that has captivated astronomers. This is the puzzle at the heart of the dark star hypothesis. And in the chapters to come, we will explore how normal stars formed, how Webb changed our expectations, how dark matter interacts with the cosmos, how dark stars would live and shine, how the evidence is being gathered, and what it all means for the future of astronomy. To understand why the discoveries from the James Webb Space Telescope are so surprising, we need to revisit the traditional picture of how the first stars formed. For decades, astronomers built a coherent, elegant narrative about the universe's early history. This narrative came from combining theory, simulations, and limited observations, and for many years it seemed to make perfect sense. According to that story, the first stars were born out of simple ingredients and straightforward processes. They were the universe's first engines of light and structure, and their appearance marked a turning point in cosmic evolution. Picture the universe after the Big Bang. In the first few minutes of cosmic time, the universe was unimaginably hot and dense. But as it expanded, it cooled rapidly. Protons, neutrons, and electrons began to combine into the first atoms. These atoms were almost exclusively hydrogen and helium, with only trace amounts of lithium. There were no heavier elements, because heavier elements can only be formed inside stars, and stars did not yet exist. For hundreds of thousands of years, the universe remained a dim, cooling sea of gas. Light traveled freely only after the cosmic microwave background was released. But at the human level of perception, the universe was dark. No stars shone, no galaxies sparkled, and no planets circled. It was a silent, drifting ocean of primordial matter. Eventually, gravity began to sculpt this ocean. Even small irregularities in the density of matter were amplified over time, as regions slightly denser than their surroundings attracted more material and grew even denser. These tiny fluctuations seeded the first structures. Simulations showed that dark matter played a crucial role here, forming invisible halos where normal matter collected. Within these halos, hydrogen and helium gas began to collapse, compress, and heat up. As the gas contracted further, it formed dense cores. These cores grew hotter and more compact until nuclear fusion ignited. At that moment, the first stars were born. These stars were known as Population 3 stars, and they held a special place in cosmic history. The early universe set the stage for these stars to be different from the ones we see today. Modern stars, like our own Sun, form in environments enriched with heavier elements such as carbon, nitrogen, oxygen, and iron. These elements act like coolants, allowing gas clouds to fragment into smaller pieces. Today, star-forming regions create stars of a wide range of sizes, from tiny red dwarfs to massive blue giants. But in the first billion years of the universe, before any heavy elements existed, star formation followed a different pattern. Without heavier elements to help cool the gas, the collapsing clouds became hotter and more massive. Instead of breaking into many smaller stars, they often formed a few extremely large ones. This led astronomers to propose that the first stars were likely enormous, perhaps hundreds of times the mass of the Sun. These massive primordial stars would have lived fast and died young. Their intense energy output would have lit up the cosmos, reionizing the surrounding gas and transforming the environment. Their nuclear furnaces would have created the first heavy elements and scattered them across space when they exploded as supernovae. This enriched the universe, enabling later generations of stars and eventually planets to form. Every atom of carbon in our bodies, every molecule of oxygen we breathe, and every grain of iron in Earth's core can trace its origins back to the explosions of these early stars. In this way, the first stars were architects of everything that came afterward. They were the engines that forged complexity from simplicity. This narrative, refined over decades, became the cornerstone of our understanding of cosmic dawn. The first stars produced the first elements, which in turn helped shape the first galaxies. Their deaths gave rise to black holes, and those black holes may have grown into the massive ones found in galactic centers today. It was a tidy and self-consistent story. It appeared in textbooks, in scientific lectures, and in simulations used by researchers. And for many years, it seemed to make perfect sense. But even before Webb, there were hints of tension. Observations from ground-based telescopes and from the Hubble Space Telescope revealed surprisingly bright galaxies at early times. Some galaxies appeared more massive or more luminous than models predicted. But the uncertainties were large, and the data were not strong enough to demand a revision. Many researchers assumed that with better observations, the pieces would eventually align neatly with the established narrative. Then Webb arrived. Its unprecedented ability to observe faint infrared light allowed it to peer back into times and places no telescope had ever reached. Suddenly, astronomers were seeing objects at redshifts of 12, 13, and 14. In cosmic terms, this meant looking at objects formed when the universe was less than 400 million years old. And what Webb found did not always match the standard picture. Some galaxies appeared too compact, some looked too bright, others seemed too chemically enriched, suggesting that many generations of stars had already lived and died, far too many to fit within the available time. And then there were the compact objects that looked like points, not galaxies. These sources appeared too bright to be ordinary stars, yet too small to be early galaxies. It was as if the universe, having followed the expected script for its first chapters, suddenly veered into unexpected territory. Something was happening that the standard model did not fully explain. To appreciate the magnitude of this surprise, imagine carefully building a model that tracks every step of a process, only to have new evidence reveal that something entirely different may have been happening alongside it. This does not contradict the entire story of the first stars, but it complicates it in ways that are profound. It suggests that the early universe may have had multiple pathways to light, not just one. Population 3 stars almost certainly existed, but perhaps they were not alone. Perhaps there were exotic actors on the cosmic stage, powered by forces and particles that we do not fully understand. Another source of tension involves the formation of supermassive black holes. Webb has found quasars powered by black holes billions of times the mass of the Sun, existing only a few 100 million years after the Big Bang. According to the standard model, it should take far longer for black holes to grow to such immense sizes. They would have to begin very small, grow slowly, and accrete matter over vast stretches of time. But the early universe simply did not provide enough time for this slow growth. Something must have accelerated the process. Something must have created seeds much larger than the remnants of ordinary stars. This puzzle led some researchers to propose the idea of direct collapse black holes, formed from rapidly collapsing gas clouds. But even direct collapse requires specific conditions and may not be sufficient to explain all observations. This is where the dark star hypothesis begins to intersect with the standard model. If dark stars existed and grew to millions of solar masses before collapsing, they would create black holes far larger than any produced by normal stars. These massive seeds could then grow into supermassive black holes quickly, solving one of the biggest mysteries in early cosmology. But to accept that possibility, scientists must first accept that the standard picture of the first stars is incomplete. Even within the traditional narrative, there were theoretical uncertainties. Simulations of population 3 star formation produce a wide range of outcomes. Some models suggest that stars formed in clusters rather than in isolation. Others propose that fragmentation could still occur even in metal-free environments. The exact mass distribution of these first stars remains unknown. Without the ability to observe them directly, astronomers relied on indirect clues. Webb, for the first time, has brought direct observations into the picture. But those observations have raised more questions than answers. Despite these challenges, the Standard Model remains a critical foundation. It explains much of what we observe, it has guided research for decades, and it provides context for understanding why the potential discovery of dark stars is so dramatic. The Standard Model tells us what should happen in a universe governed only by known physics. Dark stars represent a deviation from that story, a glimpse into processes that may have occurred only under the most extreme and primordial conditions. In this chapter, we have explored the established story of the first stars, the narrative that shaped our expectations for what Webb would reveal. It is a story of simplicity giving rise to complexity, of hydrogen and helium forming the first luminous giants, of those giants forging the building blocks of everything we see around us today. It is a story supported by decades of research, yet not immune to revision. And now, with Webb's discoveries challenging some of its predictions, we find ourselves standing between old explanations and new possibilities. In the next chapter, we will look more closely at how Webb broke the mold and why its discoveries forced astronomers to rethink some of these assumptions. The established story of the first stars was strong, but Webb has shown.
When the James Webb Space Telescope began sending back its first deep observations, astronomers immediately felt the ground shifting beneath their feet. They had expected impressive images, of course. They had expected clearer views of distant galaxies and improved measurements of early cosmic structures. But what they did not expect was that Webb would present them with objects so luminous, so massive, and so strangely compact that they simply did not fit within the existing framework of early universe theory. Webb did more than refine the picture of the cosmos, it disrupted it. To grasp the magnitude of this shift, imagine preparing for decades to open a window onto the past, convinced that you already know roughly what you will see. Generations of astronomers built models and simulations, all of them pointing toward a universe that grew slowly at first, gradually forming simple stars, then primitive galaxies, and only later the large and bright structures we see today. Everything suggested that the first few 100 million years would be a period of delicate complexity, but not one of extreme luminosity or massive structures. It was supposed to be a cosmic dawn that glowed softly, a gradual brightening rather than an immediate blaze. But as Webb examined regions of the sky at unprecedented depths, objects appeared that defied these expectations. Some galaxies Webb detected seemed far too bright for how early they existed. They would have required rapid star formation rates that pushed the limits of what physics allowed. Even more puzzling were the compact sources that appeared not as extended galaxies but as singular points of intense light. These point-like objects did not spread out across the sky as galaxies do. They concentrated their brightness into a region so small that Webb could not resolve their shapes, even with its remarkable sensitivity. This raised immediate questions. If they were stars, they were astonishingly bright. If they were galaxies, they were astonishingly small. If they were something else entirely, then astronomers had stumbled upon a category of object that had never been observed before. Each possibility carried profound implications, and the more scientists studied the data, the more they realized that the familiar paths of explanation were insufficient. One of the early surprises was how many of these bright, compact sources existed. Instead of being rare exceptions, they appeared repeatedly in deep-field images. Their abundance suggested that whatever they were not isolated anomalies. They might represent an entire class of early cosmic objects that models had not predicted. This overwhelmed the careful expectations scientists had built for decades. The early universe was supposed to be sparse, fragile, and gradual in its evolution. Yet here it was, bold and energetic, producing bright lights at a pace that no one anticipated. As researchers began to analyze the spectra of these objects, the puzzles deepened. Spectroscopy is crucial in astrophysics because it reveals the chemical composition and physical conditions of distant sources. When the light of a distant object is broken into its constituent wavelengths, unique patterns appear, each corresponding to specific elements or physical processes. But some of the spectral signatures Webb recorded did not match the fingerprints of simple early stars or early star-forming galaxies. In certain objects, the spectra suggested the presence of unusual energy sources. Some lacked the expected features of fusion-powered stars. Others possessed lines that implied large, diffuse atmospheres out of proportion to what a normal star or galaxy could produce. The realization that something fundamentally unexpected was being observed created a sense of excitement mixed with uncertainty. It was not the first time astronomy encountered surprises. Historically, new instruments often revealed phenomena that forced the scientific community to rethink long-held assumptions. But the magnitude of Webb's surprises, arriving so soon after its launch, hinted at a deeper gap in understanding. One of the early examples was the discovery of a compact bright object at redshift 14, one of the most distant ever observed. Its brightness challenged every known mechanism for energy production at such an early time. Normal nuclear fusion in stars could not explain such luminosity, at least not under the constraints of early cosmic conditions. If it were a galaxy, it would have to contain far more stars than seemed possible within the brief window of time since the Big Bang. And if it were a black hole, its mass would require an extraordinary growth rate that defied current models. This object was not alone. Several others displayed similar characteristics, pushing astronomers to revisit the assumptions built into their simulations. The timing, the luminosity, the compactness, the spectral features, everything pointed to the need for new ideas. One of the early areas re-evaluated was the assumed rate at which structures could form in the early universe. If galaxies were forming faster than expected, perhaps the conditions immediately after the Big Bang were more conducive to rapid growth than previously believed. But even if one adjusted the rate of formation, some objects remained too bright and too compact. There had to be another explanation. This is when older theoretical ideas resurfaced. Concepts that had been considered speculative for years suddenly seemed worthy of serious reconsideration. Among them was the idea of stars powered not by fusion, but by dark matter. These dark stars, if they existed, could grow far larger than normal stars and shine with luminosities that rival entire early galaxies. Their inflated sizes would make them bright, but their diffuse outer layers could cause them to appear compact in high redshift observations. They could reconcile several of the anomalies at once: the unexpected brightness, the compact point-like appearance, and the unusual spectral features. The mere possibility of such objects immediately captivated researchers. This was not a minor adjustment to early universe theory. This was a potential paradigm shift. If dark stars existed, and if Webb was seeing them, then the earliest chapters of cosmic history would need to be rewritten in fundamental ways. It would mean that dark matter, the mysterious substance that shapes galaxies through gravity alone, may have also played a role in producing the first luminous objects in the universe. But the excitement was tempered with caution. Extraordinary claims require extraordinary evidence, and the scientific community knew that Webb's data needed to be analyzed with extreme care. Every unusual spectral feature had to be verified. Every bright, compact source had to be scrutinized. Contamination from nearby sources, uncertainties in redshift measurements, and instrumental limits all needed to be ruled out before drawing firm conclusions. Researchers began conducting deeper analyses of the unusual sources,
comparing them with models of early galaxies, early black holes, and theoretical dark stars. New simulations were run to predict how dark stars would appear through Webb's instruments. Alternative explanations were examined, including the possibility of strong gravitational lensing, which could magnify distant sources and make them appear brighter. But in many cases, lensing did not fit the data. The anomalies remained anomalies. The more scientists probed, the clearer it became that Webb had uncovered something genuinely new. Whether the explanation turned out to be dark stars or some other exotic process or a previously unknown stage of early galaxy formation, one thing was certain. The early universe was not the simple and predictable environment that models had long depicted. It was dynamic, creative, and filled with surprises. These early insights marked the beginning of a profound shift in our understanding of cosmic dawn. Webb broke the mold of what astronomers expected to see. It opened a gateway to questions that had never before been answered with direct evidence. There was no longer a single straightforward narrative about how the first lights emerged. Instead, there was a richer, more complex tapestry of possibilities. The universe was revealing that it had more imagination than the models built to describe it. The discoveries did more than excite astronomers. They inspired a reassessment of fundamental questions. How did the first luminous objects form? How did dark matter interact with normal matter? How did black holes grow so rapidly? What other exotic phenomena might have existed in the cosmic dawn? These questions set the stage for a new era of exploration. In the next part of the story, the focus turns to dark matter itself and to the bold idea that it could have fueled stars at the beginning of time. To understand why the discoveries from the James Webb Space Telescope have ignited such excitement, it is essential to explore dark matter itself. Dark matter is one of the most perplexing components of the universe. It surrounds every galaxy, it shapes cosmic structure, and yet no one has ever seen it directly. The universe is full of it, and still it remains invisible. When astronomers talk about dark matter, they are referring to something that neither emits light, nor absorbs it, nor interacts with radiation in any known way. It reveals itself only through gravity, through the subtle but unmistakable pull it exerts on stars, galaxies, and the large-scale web of matter stretching across the cosmos. Imagine for a moment standing on a clear night under a sky filled with stars. Every point of light you see represents normal matter, but most of the mass shaping the universe is not visible. It does not glow or flicker. It does not burn. It simply is. When scientists calculated the motions of stars within galaxies, they realized the stars were moving far too fast to be held together by visible matter alone. Something unseen had to be providing the additional gravitational glue. This invisible mass was eventually named dark matter, not because it is made of darkness, but because it lies hidden. Dark matter's nature remains one of the greatest mysteries in physics. Decades of experiments have searched for it, trying to detect particles that could explain its behavior. The leading candidates have often been theorized as small, stable particles that interact weakly with normal matter. These hypothetical particles, sometimes called WIMPs, have the intriguing ability to annihilate when they meet their counterparts. In these annihilations, energy is released. Most of the time, this energy would be undetectable. But in the early universe, when dark matter was denser, these annihilations may have played a remarkable role. The idea that dark matter could power a star might seem strange at first, because dark matter barely interacts with normal matter. It drifts through galaxies like a ghost, influencing gravity but little else. And yet, if a forming star were located in a region with an especially high concentration of dark matter, something extraordinary could happen. As the gas cloud collapses under gravity, dark matter particles could become trapped inside it. If those particles were capable of annihilating each other, they would release heat. That heat would slow the collapse of the star, causing it to swell and expand rather than shrink into a small, dense sphere. This is the foundation of the dark star hypothesis. A dark star would look nothing like the stars we see today. The sun burns through nuclear fusion, converting hydrogen into helium at immense pressures and temperatures. A dark star, by contrast, would shine because of the heat generated by dark matter annihilation within its core. This process would be gentle enough to prevent the star from contracting too tightly. Instead of becoming a compact sphere, the star could expand into a large, diffuse form. Its surface temperature would be relatively cool, but its overall size would make it extremely bright. Dark stars could grow not just dozens or hundreds of times larger than the sun, but thousands or even millions of times larger, depending on how long dark matter continues to power them. The idea of dark stars was first proposed more than a decade ago by a small group of theorists who wondered whether dark matter could influence early star formation. Their calculations suggested that under the right conditions, dark matter-powered stars could indeed form during the first few 100 million years of the universe. These stars would be enormous giants, glowing softly with an almost ethereal light. They would grow by accumulating gas from their surroundings and by continuing to collect dark matter particles from the dense halo in which they formed. Over time, their size and luminosity would increase dramatically. One of the most remarkable predictions of the dark star model is the potential mass of these objects. While normal stars might grow to a few hundred times the mass of the Sun, dark stars could theoretically reach masses of millions of suns. Their diffuse structure would allow them to absorb enormous amounts of gas without triggering fast nuclear reactions that would disrupt their growth. Instead, they would remain puffed up and luminous for far longer than normal stars, potentially living hundreds of thousands or millions of years before collapsing. Once their dark matter supply diminished, something dramatic would happen. Without the gentle heating from dark matter annihilation, the star would no longer be able to maintain its expanded structure. The gravity would pull it inward. The collapse would be catastrophic. A dark star of millions of solar masses would not end in a typical supernova. Instead, it would collapse directly into a massive black hole. This collapse could create the seeds needed to explain the enormous black holes that Webb has found in the early universe. The timeline aligns perfectly. Dark stars form early, grow massive quickly, and collapse into black holes just in time to be detected as quasars or black hole seeds at early cosmic epochs. The possibility that dark matter could not only shape the universe gravitationally, but also fuel the first luminous objects is stunning. It challenges the notion that dark matter is a silent player in cosmic evolution. Instead, it paints a picture of a universe where dark matter briefly becomes visible, not by glowing directly, but by giving birth to stars whose light reveals its influence. If these stars existed, they would have glown brightly in the early universe, visible across vast cosmic distances. Their light, stretched by billions of years of expansion, would reach telescopes like Webb today. And that is precisely why the unusual bright objects observed by Webb have drawn so much attention. To move from theory to observation, astronomers needed to understand what signatures might distinguish a dark star from a normal star or a compact galaxy. Models predicted that dark stars would have large radii and relatively cool surfaces. Their spectra would show certain types of absorption features related to the structure of their atmospheres. These features would not match the typical light from galaxies filled with many stars. Instead, a dark star's spectrum could show wide, smooth patterns and specific absorption lines. One such predicted feature occurs around a wavelength associated with ionized helium, a clue that could reveal the presence of an extended, low-density atmosphere. When Webb detected a faint hint of this exact signature in one of the compact luminous sources, astronomers took notice. While the signal was weak, it matched what dark star models predicted. Combined with the brightness and compactness of the object, the possibility became difficult to ignore. Could it be that Webb had finally uncovered the first observational hints of a dark star, an object powered by the annihilation of dark matter in the early universe? This question electrified the field. The dark star hypothesis is compelling not only because of its novelty, but because it solves several problems at once. It explains why some early objects are so bright. It explains how black holes could grow so rapidly. It offers a new window into the behavior of dark matter. It suggests that the early universe was more diverse than previously imagined. It even provides potential clues to the particle nature of dark matter itself. If dark stars existed, then dark matter must be capable of annihilation and energy release. That would narrow the possibilities for what dark matter can be. This intersection of particle physics and cosmology is what makes dark stars so fascinating. They represent a bridge between two fields that often operate independently. On one hand, cosmologists explore the large-scale structure of the universe. On the other, particle physicists search for the tiny particles that govern the behavior of matter. Dark stars bring these scales together. They suggest that the universe, in its earliest moments, was a laboratory where the tiniest particles influenced the largest structures. The excitement does not diminish the challenges. Detecting dark stars requires exquisite observations. Distinguishing them from compact galaxies or bright stellar clusters is difficult. Spectral signals are faint, and redshift uncertainties can complicate interpretation. But the clues Webb is uncovering provide enough intrigue to warrant serious investigation. Astronomers now conduct detailed modeling, run advanced simulations, and plan future observations that may confirm or refute the existence of these exotic objects. The idea that the first stars might have been powered by a force that remains invisible to this day invites a profound sense of wonder. It suggests that the universe, even in its earliest moments, was filled with creative processes that defy simple categorization. Dark stars may or may not be real, but the pursuit of understanding them has already expanded the way scientists think about cosmic origins. The moment scientists began analyzing the unusual objects detected by the James Webb Space Telescope, it became clear that something extraordinary was unfolding. Among all the surprising discoveries in Webb's early data, a handful of compact luminous sources stood out sharply. These objects were not faint or ambiguous. They were bright, distant, and unmistakably real. What made them remarkable was that their properties lined up with predictions that had lived entirely in the realm of theory. And as astronomers looked more closely, they found features that sent a ripple of astonishment across the scientific world. The study that triggered this shift did not begin with the intention of discovering dark stars. It began as a routine analysis of Webb's deep field observations, part of a broader effort to identify the earliest galaxies and to map the landscape of cosmic dawn. One team, led by researchers who had long studied the earliest phases of the universe, was examining high redshift objects cataloged in Webb's deep exposures. These objects had cryptic numerical labels.
each one representing a measured redshift and a detected position on the sky. To most observers, the labels would have seemed like nothing more than technical identifiers, but to the scientists analyzing them, they were keys to a set of mysteries. Among the cataloged objects were several that appeared unusually bright. They included sources now known by names such as JADES, GSZ-140, and its siblings. These designations may feel abstract, yet they describe some of the most distant objects ever seen, their light having traveled more than 13 billion years to reach Earth. At first, these objects were assumed to be compact early galaxies, perhaps forming their first stars. But when scientists examined the detailed data, the story grew more complex. The first surprise came from the object's brightness. They were far too luminous for their presumed size. For a galaxy to shine with such intensity so early in cosmic history, it would need to host an enormous burst of star formation, with stars forming at a pace that exceeded theoretical limits. Such starbursts are rare even in the modern universe. In the early universe, they would be exceptional. Yet these objects appeared not to be extended galaxies bursting with stars, but concentrated points of light. This defied easy explanation. The shapes were compact, unresolved even by Webb's extraordinary resolution. This suggested an object smaller than a typical galaxy, but still shining with incredible power. The next surprise came when the researchers analyzed the spectra. Webb's instruments can break the light from distant objects into spectra that reveal the physical conditions and chemical composition of the source. For distant, early cosmic objects, spectra are challenging to obtain because the light is faint and stretched by enormous redshifts. Yet even with these challenges, Webb recorded enough information to reveal a few critical features. One of these was a faint but distinct absorption line associated with ionized helium. This line appears at a wavelength that corresponds to 1640 angstroms before redshift, a feature long predicted to be present in the atmospheres of dark stars. This was not a random coincidence. The presence of ionized helium absorption at the scale and strength observed cannot be easily produced by small galaxies or by normal stars. In most cases, such features arise when the object has a large, diffuse atmosphere, heated in an unusual way. Normal stellar atmospheres, particularly those in massive early stars, tend to show other features first. The appearance of this particular absorption line at this faint but detectable level was exactly the kind of signature theorists had suggested might betray the presence of a dark star. The study's authors, cautious and meticulous, did not leap to conclusions. They presented the data with care, noting that the signal-to-noise was low and that further confirmation was needed, but they also acknowledged that the object's properties matched predictions of supermassive dark stars closely enough to merit serious consideration. This was not an idle suggestion. It was a hypothesis grounded in specific, measurable features. The researchers outlined several possible interpretations. The object could be a compact star-forming galaxy, or it could be a peculiar early star cluster, or it could be the long-sought dark star. What made the dark star explanation compelling was how neatly it resolved multiple anomalies at once. A supermassive dark star could easily be bright enough to explain the observed luminosity. Its diffuse surface would create absorption patterns matching the spectral features. Its size and structure could make it appear point-like even to Webb, and its age, inferred from the redshift, placed it firmly within the epoch where dark stars were predicted to exist, if they exist at all. Still, scientists understood the importance of caution. Astronomy is full of examples where initial interpretations evolved into more grounded conclusions. A faint spectral line could be an artifact. A compact source could be a small galaxy whose true shape was blurred by observational limitations.
Therefore, the study's authors laid out a careful roadmap for future observations. They highlighted the need for deeper spectra, more accurate measurements of the object's sizes, and a detailed comparison with galaxy models. But even with this caution, the scientific community was captivated. The possibility that one of these bright, compact objects might be a dark star was breathtaking. For decades, dark stars had been little more than a clever theoretical exercise. They were discussed in niche corners of astrophysics, considered interesting but unlikely. Yet here was real data from the most powerful space telescope ever built, showing signs that aligned with the predictions. Around the world, theoretical astrophysicists took notice. New models were hastily computed. Teams ran simulations to determine how dark stars would appear through Webb's instruments. Others tested alternative explanations, including gravitational lensing, unusual star clusters, or early quasars disguised by their surroundings. But the more these scenarios were explored, the more gaps they revealed. Some required contrived conditions. Others could not reproduce the spectral features. A few matched the brightness but not the compactness. None provided as seamless an explanation as the dark star model. One object in particular captured attention. It exhibited not only brightness and compactness, but that faint ionized helium signature. While the signal was weak, the feature was located exactly where theorists had predicted it should be. It was the kind of discovery that forces scientists to reconsider the boundaries between theory and observation. For years, dark stars seemed too exotic to be detected. Now, suddenly, one might have been hiding in the data all along. As discussion spread through conferences, research groups, and online astronomy forums, the tone of the conversation shifted. The scientific community began to treat dark stars not as an outlandish idea, but as a genuine possibility that deserved further investigation. Researchers had long argued about the nature of dark matter and how it might interact. Now they had a potentially observable phenomenon that tied cosmic evolution directly to dark matter physics. This study did more than raise questions about one object. It opened a new chapter in the exploration of the early universe. If one dark star existed, others might exist as well. Webb's deep fields might contain more such compact points of light waiting to be analyzed. And if dark stars were common, they could have influenced early cosmic evolution far more dramatically than anyone had imagined. They could have reshaped early galaxies, seeded black holes, and even altered the way radiation propagated in the primordial cosmos. This study was a single step, but it was a monumental one. It reminded scientists that the universe still holds secrets that challenge even the most sophisticated models. It demonstrated that observations can leap ahead of theory, revealing phenomena that demand new explanations. And it rekindled a sense of wonder that belongs at the heart of astronomy, a reminder that the cosmos is far richer, stranger, and more imaginative than the models built to describe it. The implications of this study go far beyond one object or one dataset. They lead directly to deeper questions about how dark stars could form, how they would behave, and how they could grow so massive. And those questions bring us into the next part of this story, where the internal mechanisms of a dark star take center stage. To understand why the possibility of dark stars is so compelling, it helps to imagine what such an object would be like from the inside out. A dark star is not simply a normal star with a strange energy source. It is a fundamentally different kind of structure, shaped not by nuclear fusion, but by the invisible motions of dark matter within its core. To explore how dark stars would work, we must step back into the earliest moments of cosmic history, a time when the universe was dense, smooth, and filled with both visible and invisible matter drifting through a rapidly expanding space.
In those early times, dark matter played a crucial role in forming the first gravitational wells. While normal matter was influenced by heat, radiation pressure, and electromagnetic interactions, dark matter ignored those forces entirely. It felt only gravity. That meant it began to clump early, forming halos that acted like gravitational traps. These halos were the skeleton of cosmic structure. Normal matter, made of hydrogen and helium gas, eventually fell into these halos, collapsing under gravity and forming the seeds of the first stars. The idea of a dark star begins when a collapsing cloud of gas finds itself inside a halo rich in dark matter particles. As the gas cools and contracts, dark matter particles drift into the same region. Because dark matter interacts so weakly, it passes through the gas easily, gathering near the center as gravity pulls everything inward. Some theoretical models suggest that these particles can accumulate in significant numbers. If the dark matter is made of particles that annihilate when they collide, the center of the collapsing cloud becomes a site of energy production. Every annihilation releases small bursts of heat. Under normal circumstances, the heat produced inside a forming star comes from the gravitational collapse itself. As the cloud contracts, it becomes hotter and denser until nuclear fusion finally ignites. But if dark matter annihilation provides enough heat early in the process, it can slow or even halt the collapse before fusion begins. The gas becomes warm, but not hot enough for fusion. And because the heating is steady, the core resists further contraction. The result is a star that swells instead of shrinking. This inflation leads to the formation of a structure unlike any star we are familiar with. Instead of being compact and intensely hot at its core, the early dark star becomes large, cool, and diffuse. It continues to shine, but not because atomic nuclei are fusing. Its light comes from the energy deposited by dark matter particles annihilating deep within. This energy radiates outward, heating the gas and creating a gently glowing object whose surface temperature might resemble a warm ember rather than a blazing fire. Despite this low surface temperature, dark stars can be extremely bright. Their immense size means that even at relatively cool temperatures, they emit large amounts of light. In some models, the first dark stars could be as large as the orbit of Earth around the Sun, or larger still. Their diffuse outer layers would make them appear almost ethereal, like glowing spheres of mist. They would not flicker or pulsate rapidly as some massive stars do. Instead, they would shine steadily, their brightness determined by the rate of dark matter annihilation in their centers. As long as dark matter continues to fall into the star and annihilate, the star can maintain this inflated state. During this phase, the star continues to accrete normal matter from its surroundings. Gas in the early universe was plentiful, and because the dark star is large and gravitationally attractive, it gathers material efficiently. Unlike normal stars, which must maintain a delicate balance between gravity and internal pressure from fusion, a dark star's internal heat source is gentle and steady, allowing it to grow without triggering explosive reactions. This is one of the most striking differences between dark stars and normal stars. In a normal star, additional mass increases the pressure and temperature of the core, which accelerates fusion. This leads to a feedback loop. A sufficiently massive star burns through its fuel faster and lives a shorter life. But a dark star, powered by dark matter, does not rely on fusion at all during its growth phase. It can add mass without overheating. This allows it to grow far larger than any normal star could before fusion becomes unstable. The growth phase of a dark star may last hundreds of thousands to millions of years. During this time, the star can reach astonishing masses.
Models suggest that dark stars could grow to thousands, hundreds of thousands, or even millions of solar masses, depending on how much dark matter remains available to fuel their expansion. Such masses are unheard of in traditional stellar evolution, making dark stars truly unique cosmic beings. At some point, however, the supply of dark matter begins to diminish. Dark matter annihilation relies on particles colliding. As the dark matter near the star's core gets used up, the rate of annihilation declines. If fresh dark matter cannot be supplied quickly enough, the heating decreases. Slowly, the balance that kept the star inflated begins to shift. Gravity, always persistent, takes over once more, pulling the star inward. As the star contracts, its core temperature rises. If the star has grown to enormous size, the compression becomes catastrophic. In smaller dark stars, contraction might ignite nuclear fusion for a brief final phase. But in the most massive ones, those with millions of solar masses, the contraction leads to direct collapse. The star collapses inward faster and faster, its core unable to support the weight of its colossal mass. The collapse continues until a black hole is born. This process is remarkable because it creates a massive black hole in one step. Normal stars form black holes only after they have burned through their fuel and exploded as supernovae. Even then, they usually only produce black holes a few times the mass of the Sun. Dark stars, by contrast, can collapse into black holes thousands or millions of times more massive. These black holes would be the perfect seeds for the supermassive black holes that Webb has discovered existing very early in cosmic history. This mechanism solves one of the most difficult puzzles in cosmology. How could black holes reach billions of solar masses so quickly after the Big Bang? If they began as massive seeds formed from collapsing dark stars, the timeline becomes much easier to understand. They would start their growth already enormous, needing only a few 100 million years to become the luminous quasars seen at high redshifts. Another fascinating aspect of dark star physics is the interaction between dark matter and normal matter. Dark matter barely interacts with normal matter, yet in a dark star, the two are inseparably linked. The normal matter forms the visible structure of the star, while the dark matter, hidden and undetectable directly, acts as the power source. This blending of visible and invisible matter within a single structure creates a star that exists at the intersection of astrophysics and particle physics. It is a stellar object that cannot be understood without both. From an observer's perspective, dark stars would appear cooler than typical young massive stars. Instead of bluish light, they might glow with reddish or golden hues. But their brightness would be immense. They would dominate the early sky wherever they formed. In simulations, dark stars shine steadily, without the violent fluctuations or explosive outbursts characteristic of normal massive stars. Their light would be steady, calm, and persistent, a cosmic lamp fueled quietly by the interactions of unseen particles. Theoretical models also suggest that dark stars might be surrounded by halos of ionized gas, caused by radiation escaping from their vast atmospheres. This gas could produce distinctive absorption features in the star's spectrum. One such feature related to singly ionized helium is precisely what Webb detected faintly in one of its compact high-redshift objects. These spectral clues are among the most important pieces of evidence that scientists are now studying carefully. Even with these promising predictions, dark stars remain theoretical. Observing them directly is a formidable challenge. The cosmos is ancient, and dark stars, if they existed, would have lived and died more than 13 billion years ago. All that remains now is their light, stretched thin by cosmic expansion and perhaps the massive black holes into which they collapsed. But for the first time in history, a telescope with the sensitivity of Webb can detect hints of these early giants, preserved like fossils in the light of the distant universe. The behavior of dark stars reflects a universe that was more exotic and varied than once believed. Their existence would mean that the early cosmos explored multiple pathways for producing light. Normal stars may have formed alongside dark stars, each contributing to cosmic evolution in different ways. Together, they would have shaped the galaxies, black holes, and cosmic structures that followed. This understanding of how dark stars work provides a foundation for interpreting Webb's discoveries. It offers a possible explanation for the brightness, the spectra, and the compactness of the mysterious objects now being observed. And it leads naturally into the next step in the story, where we explore how these possibilities could reshape our understanding of the early universe itself. To appreciate the profound implications of dark stars, it helps to imagine the early universe not as a simple, predictable environment, but as a place filled with possibilities that our earlier models never fully captured. When scientists first developed the standard picture of cosmic dawn, they envisioned the universe that behaved in an orderly way. As hydrogen and helium gas cooled, it clumped together into denser regions, eventually forming the first stars through a familiar process of collapse, heating, and ignition. Those stars then produced the first heavier elements, enabling later generations of stars and galaxies to form. It was a straightforward, elegant progression. But if dark stars existed, this early universe would look dramatically different. Instead of a cosmos illuminated slowly and cautiously by the first generations of fusion-powered stars, the earliest epochs might have glowed with immense, diffuse giants powered by dark matter. These stars would not have been rare curiosities. In some regions of space, they might have been common. Their presence would have reshaped the timing, appearance, and evolution of everything around them. It is helpful to picture the early universe as a vast, mostly empty expanse filled with clouds of primordial gas and halos of dark matter. These halos were the seeds of structure, drawing normal matter into their gravitational wells. If a dark matter halo was especially dense, it could trap more material and grow more quickly. In these densest halos, normal star formation might have occurred alongside the formation of dark stars. The interplay between these processes could produce a rich variety of luminous objects, not just one type. The existence of dark stars would alter the pacing of cosmic evolution. Normal population 3 stars formed quickly and died quickly. Their lives were intense and brief, lasting only a few million years at most. They exploded violently, scattering heavy elements into space and paving the way for later stars and galaxies. But dark stars would follow a different timeline. They would live longer, sometimes hundreds of thousands or even millions of years, growing steadily throughout their lifetimes. This extended growth would give them time to reach extraordinary sizes, far larger than typical early stars. Because they grew so large, dark stars would influence their surroundings in ways that smaller stars could not. Their radiation would ionize gas across vast regions. Their gravitational pull would alter the flow of matter around them. Their eventual collapse would create massive black hole seeds, long before most normal stars had even finished forming. This would set the stage for some of the earliest supermassive black holes the universe has ever produced. The presence of dark stars would also create pockets of the universe that evolved differently from others. Where dark matter densities were high, dark stars could flourish. In regions with less dark matter, normal star formation would dominate. This would create a patchy, uneven landscape during cosmic dawn. Some areas of the universe would be dominated by enormous glowing giants, while others would be filled with clusters of smaller, fusion-powered stars. This unevenness could help explain why Webb sees such a surprising diversity of objects at high redshifts. Instead of a uniform progression from simple stars to complex galaxies, the early universe might have been a mosaic of different evolutionary pathways. In this reimagined early cosmos, dark stars would not simply replace normal stars, they would coexist with them, influencing each other in subtle and profound ways. Their radiation might suppress star formation in nearby regions, or provoke it by heating and reshaping the surrounding gas. Their gravitational influence could draw material into dense pockets that later formed primitive galaxies. Their collapse into black holes could seed the centers of nascent galaxies, accelerating their growth. This multi-path evolution contrasts sharply with earlier models of cosmic dawn. Those models assumed that the earliest stars were uniformly massive, uniformly short-lived, and uniformly important. But dark stars introduced diversity into the earliest stages of the universe. They introduce a new category of objects that could dominate certain environments while remaining absent in others. This diversity helps explain why some regions of the early universe seem more evolved than others. It helps explain why some galaxies detected by Webb appear unusually compact and bright, while others appear more diffuse or chemically enriched. This new picture also helps resolve a long-standing puzzle: the timing of reionization. Reionization was the period when the first luminous objects produced enough energetic radiation to strip electrons off hydrogen atoms throughout the universe, turning the intergalactic medium from neutral to ionized. The timing of this process has been difficult to reconcile with the number of stars thought to exist in the early universe. If dark stars contributed even a modest amount of radiation during their long lifetimes, they could have significantly aided the reionization process. Their immense sizes and steady glow would have helped bathe the surrounding universe in light during a period when normal stars alone may not have been sufficient. Another major implication involves the earliest black holes. Webb has uncovered quasars powered by supermassive black holes at astonishingly high redshifts. These black holes are too massive to have grown from the remnants of normal stars alone within the available time. Dark stars solve this problem elegantly. Their direct collapse into massive black holes produces seeds large enough to explain the rapid growth of quasars. Instead of starting from small black holes only a few times the mass of the Sun, early black holes could have begun already tens of thousands or even millions of solar masses. This shift in black hole seeding has a cascading effect on galaxy formation. Galaxies with early central black holes can form stars more rapidly because the black hole's gravitational influence helps concentrate gas. This can lead to surprisingly mature galaxies appearing earlier than expected, which is precisely what Webb has observed. Some of the earliest galaxies in Webb's images appear more massive, more luminous, and more chemically complex than theory predicted. Dark stars could be one of the missing pieces that explain this unexpected maturity. Even the spectral signals detected by Webb make more sense when viewed through the lens of dark stars. The faint ionized helium absorption line detected in one of the compact sources, while not definitive on its own, becomes far more meaningful if dark stars existed. It fits into a larger pattern of objects that are too bright, too compact, and too unusual to be explained by ordinary star formation. It suggests that at least some early objects were not galaxies, but immense, exotic stars shining quietly in the dark. The possibility that the early universe contained these strange giants also challenges the way scientists interpret observations. Traditionally, extremely bright, high redshift objects were assumed to be galaxies. With dark stars in the picture, that assumption can no longer be automatic. Some fraction of these compact, bright objects might be individual stars, not collections of them. This forces researchers to reevaluate luminosity functions, galaxy counts, and early structure formation models. It also encourages scientists to think more creatively about the physics of the early universe. Dark stars blend cosmology and particle physics in ways that few other objects do. They suggest that the physics governing the early universe may have included processes rarely seen today. They remind us that the universe at its beginnings was governed by conditions fundamentally different from those of the present. High dark matter densities, rapid structure formation, and intense environmental variations all contributed to a cosmological landscape where exotic objects could thrive. The existence of such objects would not diminish the importance of normal population 3 stars. Those stars would still have played a crucial role in forming heavy elements and shaping the early galaxies. But dark stars would add depth and complexity to the story. They would reveal that cosmic dawn was not a uniform glow, but a vibrant, multi-layered period filled with diverse and powerful structures. If dark stars existed, they were part of the universe's creative freedom during its earliest chapters. Their light would have mingled with the light of the first fusion-powered stars, together piercing the darkness that had dominated since the Big Bang. They would have left behind massive black holes that grew into the monstrous quasars we see today. They would have influenced the distribution of gas and dark matter, affecting the tapestry of galaxies that followed. In this way, dark stars offer a new narrative for cosmic dawn. They do not replace the old story, they expand it. They push the boundaries of what might have been possible, and they remind us that the universe is not limited to the processes we already understand. It may have taken paths that still challenge our imagination. When astronomers first considered the possibility that some of the compact, bright objects detected by the James Webb Space Telescope might be dark stars, the idea immediately sparked excitement. But scientific excitement always comes paired with skepticism. Every intriguing signal, every unusual measurement, and every unexpected observation must be tested, questioned, and challenged before it can be accepted. The evidence for dark stars, while compelling in parts, also comes with limitations, uncertainties, and the need for careful interpretation. Understanding these strengths and cautions is essential to appreciating where the field stands today. The heart of the evidence lies in a handful of key observations: unexpected brightness, compactness, unusual spectral features, and the timing of their appearance. None of these alone can prove the existence of dark stars, but together they form a constellation of clues that cannot be easily dismissed. Brightness is the first clue. Several of the objects discovered by Webb are extraordinarily luminous, far more so than expected for their age and presumed nature. At redshifts of 13 or 14, the universe was only a few 100 million years old. According to traditional models, galaxies at that time should be small and faint, composed primarily of short-lived massive stars just beginning to form heavier elements. Yet Webb's data reveals objects so bright that they challenge these expectations. To produce such light, a normal galaxy would need an enormous number of stars forming simultaneously, but the compactness of these objects contradicts that interpretation. They're point-like, not extended. If a galaxy were forming stars so rapidly that it produced this much light, it should appear larger, fuzzier, and more spread out. Instead, these sources remain tight, unresolved, and almost star-like. Compactness is the second major clue. Webb has extremely sharp vision in the infrared. When an object appears unresolved, it means its size is smaller than the telescope's resolution at that distance. Normal galaxies at these redshifts are expected to span hundreds or thousands of light years, which would appear as slightly extended smudges even to Webb. But these anomalous objects appear essentially as points. The simplest interpretation is that they are either extremely small galaxies or individual stars. And if they are individual stars, their brightness becomes even more difficult to explain using ordinary stellar physics. No known type of early star can be both so bright and so compact at such an early period, unless something unusual is powering it. Then there are the spectra, perhaps the most tantalizing but also the most delicate pieces of evidence. In one of the brightest compact sources, astronomers detected a faint signature corresponding to singly ionized helium. This is not a common feature in normal stars at such distances. The line is faint, but its location is exactly where theorists predicted it should be for a dark star with a large diffuse atmosphere. In a dark star, the energy source at its core would heat the outer layers differently than in a fusion-powered star, producing distinctive absorption patterns. The presence of this helium signature does not prove the object is a dark star, but it fits the model surprisingly well.
However, it is crucial to recognize the limitations of this spectral evidence. The signal-to-noise ratio is low, meaning the feature is barely above the background noise. In astronomy, faint signals can sometimes arise from random fluctuations, instrumental artifacts, or data processing issues. Until deeper spectra are taken with clearer resolution, this helium feature must be interpreted cautiously. It serves as an intriguing hint rather than a definitive measurement. Another important observation is the timing. These compact, bright objects appear at redshifts where dark stars are predicted to exist. According to theoretical models, dark stars would form in the earliest halos before the first heavy elements had time to accumulate. They would shine during the era when the universe was still young and pristine. The fact that these mysterious objects appear precisely in this window strengthens the case, but does not eliminate all other explanations. Timing alone cannot confirm their nature, but it supports the broader pattern. Alongside these strengths, several sources of caution must be considered. One of the biggest challenges is distinguishing a dark star from a very small, very bright galaxy. Even a compact galaxy containing a tight cluster of massive stars could appear point-like at high redshift. Such galaxies might form rapidly under certain extreme conditions, creating an intense burst of brightness. Some theoretical models suggest that early galaxies could form more quickly than previously believed, especially if gas collapsed efficiently in dense halos. If this is happening, then some of the bright compact sources might simply be unusually efficient early galaxies, rather than exotic dark stars. Complicating this interpretation is the possibility of contamination or blending. High redshift observations are difficult. Light from nearby sources can overlap. Background or foreground objects can distort the shape or spectrum of a distant source. Webb's instruments are incredibly sensitive, but they are not immune to confusion. Astronomers must carefully disentangle these possibilities before assigning a definitive identity to any compact source. Another caution comes from the presence of oxygen detected in one of the candidate sources. Oxygen is a heavy element created by nuclear fusion inside stars. If a compact, bright source contains oxygen, it may indicate that it is part of a galaxy rather than an isolated star. A dark star should form from pristine hydrogen and helium. If oxygen is present, it could mean that the object is not a pure dark star, but perhaps a galaxy with complex internal structure or a system undergoing merger events. However, this does not rule out dark stars entirely. It is possible that a dark star could sit inside or near a metal-enriched region, or that galaxies could host dark stars alongside normal stars. But the oxygen detection complicates the interpretation.
A further challenge lies in the uncertainty of redshift measurements. While Webb provides extremely accurate redshifts, the faintness of the spectra at such distances means that small errors can sometimes occur. Redshift determines the object's age and distance. If the redshift is slightly off, the interpretation of the object's brightness and spectral features changes. Astronomers must obtain repeated, high-precision measurements to confirm that these sources truly lie as far back in time as initial data suggests. Then there is the issue of lensing. Gravitational lensing occurs when a massive object, such as a cluster of galaxies, lies between a distant source and the observer. The mass of the intervening object bends and magnifies the light of the distant source, making it appear brighter than it truly is. If any of the compact bright sources are gravitationally lensed, they might not be as luminous as they appear. Lensing could make a faint compact galaxy look like a bright point source. For this reason, researchers must carefully examine the surrounding regions for signs of lensing. In some cases, lensing can be ruled out because there is no nearby massive object. But in other cases, small lensing effects are harder to detect, leaving uncertainties that must be resolved. Despite these cautions, the pattern emerging from Webb's data continues to intrigue scientists. It is not a single anomaly or a single measurement that raises the possibility of dark stars. It is the combination of brightness, compactness, spectral hints, timing, and consistency with long-standing theoretical predictions. This combination makes dark stars an attractive interpretation, even if it remains unproven. The cautionary aspects are not weaknesses. They are part of the scientific process. They reflect the rigor with which astronomers approach extraordinary claims. Each anomaly must be addressed, each alternative interpretation explored. Only through this process can the community move from speculation toward confidence. The uncertainties do not diminish the excitement. Instead, it heightens the sense of possibility. The early universe is notoriously difficult to study, and every new observation has the potential to reshape our understanding. Even if some of these compact bright sources turn out to be small galaxies or unusual star clusters, the fact remains that Webb has revealed a population of objects that challenge existing models. This alone is significant. It means the early universe was more diverse, more dynamic, and more complex than previously imagined. But if even one of these objects is a dark star, the implications would be enormous. It would confirm that dark matter is capable of heating matter through annihilation. It would validate decades of theoretical work. It would show that the first stars in the universe may have been radically different from those that followed. And it would provide crucial clues about the nature of dark matter itself, a mystery that has eluded scientists for generations. The evidence is tantalizing but incomplete. The cautions are serious but not disqualifying. The field stands at a crossroads, with compelling possibilities waiting to be tested. Future observations will bring clarity, but for now, the early hints from Webb invite us to imagine that the early universe may have harbored objects more exotic and awe-inspiring than anything we have seen before.
As soon as the first surprising signals emerged from the James Webb Space Telescope's deep-field observations, astronomers realized that they were standing at the threshold of a new scientific frontier. But the discovery of unusual objects is only the beginning. The real work lies in confirming what these objects truly are, understanding what physical processes drive their behavior, and integrating that knowledge into the broader story of the universe's early evolution. The next phase of research is therefore critical, and it involves a combination of deeper observations, improved simulations, new theoretical models, and collaborative effort across multiple scientific disciplines. One of the most pressing tasks is to obtain deeper and more precise spectra of the candidate objects. The faint helium absorption feature that hints at the presence of a dark star is a tantalizing clue, but its low signal-to-noise ratio means it must be measured again with higher sensitivity. Webb spectrographs are capable of producing such data, but doing so requires longer exposures and more focused observations. Astronomers will need to dedicate significant amounts of telescope time to probing these sources in detail, carefully analyzing their spectral fingerprints to confirm whether the helium line is real and to search for other telltale signatures. A deeper spectrum would allow researchers to separate noise from genuine signals, revealing not just one absorption line, but the broader pattern of features that define an object's physical structure. A dark star's diffuse atmosphere would create a distinctive set of absorption characteristics. These could include broad spectral shoulders, subtle dips at certain wavelengths, and a relative absence of heavy element lines that would appear in compact galaxies. If future observations revealed this full pattern, the case for dark stars would grow far stronger. In addition to improved spectra, astronomers need precise measurements of the object's sizes. Determining whether an observed source is an unresolved point-like object or a small but extended galaxy is essential. High-resolution imaging techniques, including careful analysis of the point spread function, can reveal tiny deviations that indicate whether a source has measurable spatial extent. By comparing the observed shapes to models of Webb's instrument response, researchers can distinguish between single stars, star clusters, and compact galaxies with far greater confidence. Another crucial step involves verifying the distances of these objects. Redshift measurements are the backbone of high redshift astronomy. They allow researchers to determine how long the light has traveled, how rapidly the universe was expanding at the time it was emitted, and what physical processes were likely occurring in that era. The faintness of these sources means that initial redshift measurements carry some uncertainty. Obtaining repeated and more accurate redshifts will confirm whether the objects truly reside at the extreme distances suggested by early observations. If the redshifts hold, the case for exotic origins becomes even more compelling. Alongside observational efforts, theoretical research is advancing rapidly. Teams of astrophysicists are running simulations to predict how dark stars of various sizes and masses would evolve over time. These simulations incorporate different dark matter particle properties, different halo environments, and different accretion scenarios. By comparing the predicted behavior of dark stars to the observed properties of the Webb candidates, researchers can test how plausible it is for dark stars to form and survive under realistic conditions. Theoretical models are also being updated to explore the interplay between dark stars and their environments. For example, how would radiation from a dark star affect nearby gas? Would it suppress or enhance local star formation? Could dark stars exist inside primitive galaxies, or would they form only in isolation? How would the collapse of a dark star into a massive black hole influence subsequent cosmic evolution? These questions are essential for understanding whether dark stars could be part of a coherent narrative of early structure formation, or whether they would create inconsistencies in other areas of cosmic history. Another exciting area of research involves exploring the potential diversity of dark stars. Early models often focused on a narrow set of possibilities, dark stars powered entirely by dark matter annihilation. But newer ideas suggest a broader range of hybrid objects. Some stars might begin as dark stars, then transition into fusion-powered stars after dark matter becomes depleted. Others might form as fusion stars, but later experience bursts of dark matter heating if they pass through dense regions of a halo. Still others might be powered by a combination of fusion and dark matter interactions simultaneously. These hybrid models expand the range of possible observational signatures and help explain the diversity of early objects that Webb is revealing. Of course, dark stars are not the only explanation being considered. Researchers are actively exploring alternative scenarios that could produce similarly bright and compact objects. These alternatives include unusually efficient early star clusters, direct collapse galaxies, or early quasars with obscured accretion disks. Each of these possibilities has strengths and weaknesses. Some can explain the brightness, but not the spectra. Others can explain the compactness, but not the timing. The goal of ongoing research is not to dismiss alternative explanations, but to refine them, test them, and determine which ones can truly match the data. Another important part of the next phase involves statistical studies. If dark stars existed, they would not appear randomly across the sky. They would form preferentially in the densest early dark matter halos, which themselves have predictable distributions. By mapping the frequency and positions of compact bright objects in Webb's deep fields, scientists can compare the observed distribution to predictions from dark star models. A match would strengthen the case for dark stars. A mismatch would suggest alternative explanations. The rapid pace of new data from Webb means that the field is evolving quickly. Each new deep field image reveals more compact sources. Some look similar to the initial candidates, others exhibit different properties, challenging researchers to refine their classifications. Cataloging these objects, measuring their colors, analyzing their spectra, and comparing them to models will gradually build a clearer picture of what is happening in the earliest epochs. Future observatories will also play a vital role. The Nancy Grace Roman Space Telescope, set to launch in the coming years, will survey vast areas of the sky with high sensitivity. Its wide-field capabilities will complement Webb's deep, narrow-field observations. Meanwhile, ground-based observatories equipped with massive mirrors and adaptive optics systems will provide follow-up data in wavelengths Webb cannot access. These collaborative approaches will help confirm or refute dark star candidates. Longer-term missions, such as proposed next-generation infrared or ultraviolet telescopes, will go even further. If dark stars exist, these future instruments could detect them more clearly and in greater numbers. They could help create a census of early universe objects that includes not just galaxies and quasars, but exotic stellar giants powered by dark matter. Ultimately, the question of what comes next in the research is not limited to studying a few bright objects. It is about building an entire framework for understanding an era of cosmic history that has only just begun to be revealed. It is about bringing together observations, theory, modeling, and experimentation to determine whether dark stars were real actors in the early universe. And it is about recognizing that we are living in a moment of scientific discovery where fundamental assumptions are being tested and new ideas are emerging. The next steps in the research are clear. Gather better data, refine models, test alternatives, and explore the consequences of each possibility. But the broader goal is even more profound. It is to uncover the true nature of the universe during its earliest chapters. Whether dark stars turn out to be real or whether another explanation emerges, the pursuit itself is transforming our understanding of cosmic dawn and shaping the next era of astronomy.
The possibility that some of the earliest luminous objects in the universe were powered by dark matter rather than by nuclear fusion carries profound implications. If even one dark star existed, the consequences ripple outward across cosmology, astrophysics, and particle physics. It would not simply add a new type of star to the cosmic inventory, it would reshape our understanding of how the universe works, how its structures formed, and what dark matter truly is. In many ways, the idea of dark stars forces us to reconsider the very fabric of early cosmic history. One of the most important implications concerns the nature of dark matter itself. For a dark star to form, dark matter must be made of particles that can annihilate when they interact. This means dark matter cannot be a completely inert substance. It must have some form of interaction that produces energy when two particles meet. This immediately rules out certain classes of dark matter candidates and strengthens the case for others. If dark stars are real, then dark matter is likely composed of particles that behave similarly to the hypothetical WIMPs,
weakly interacting massive particles that many theorists have long considered promising candidates. These particles would gather in the centers of forming stars, collide, and release energy in the form of heat. This would be the first astrophysical evidence showing that dark matter can do more than influence gravity. It would reveal that dark matter participates in the universe in more subtle and complex ways. It would mean that dark matter is not just an invisible scaffolding for galaxies, but an actor capable of shaping luminous structures directly. For decades, scientists have built sensitive detectors deep underground, hoping to catch a glimpse of dark matter interacting with ordinary matter. None of those detectors has yet discovered a conclusive signal. But dark stars would offer a different kind of detection, an indirect one, encoded not in a laboratory instrument, but in the distant light of the early universe. The implications extend beyond particle physics into the realm of cosmic structure formation. One of the great puzzles in astronomy is the existence of supermassive black holes at extremely high redshifts. Webb has observed quasars shining less than 1 billion years after the Big Bang, powered by black holes that weigh billions of times more than the Sun. According to traditional models, black holes grow slowly from the remnants of massive stars. Even with rapid accretion, it should take far longer than a few 100 million years to reach such staggering masses. This timeline problem has persisted for years and has motivated numerous alternative theories, including direct collapse black holes and runaway star formation in dense regions. Dark stars provide a compelling solution. If a dark star grows to 1 million solar masses or more before collapsing, it would form a black hole already massive enough to serve as the seed for a quasar. Instead of beginning with a tiny black hole, a few times the mass of the Sun, the universe could begin with a black hole tens of thousands or millions of times larger. Such a seed would have no difficulty growing rapidly into a supermassive black hole within the first billion years. This elegantly resolves the mystery of how quasars appear so early in cosmic history. It replaces the need for fine-tuned growth scenarios with a natural, physically motivated process. The influence of dark stars on galaxy formation is equally significant. Black holes are not passive objects. They influence their environments through powerful radiation, jets, and winds. A massive black hole at the center of an early galaxy could accelerate star formation or regulate it. This interaction can create galaxies that are surprisingly mature at early times, which is exactly what Webb has observed. Some early galaxies appear more developed than expected, containing heavy elements and complex structures long before standard models predicted. The presence of early massive black holes could explain this accelerated evolution. If those black holes formed from collapsing dark stars, then dark matter indirectly shaped the structure of galaxies by creating the conditions for rapid evolution. Another important implication relates to the reionization of the universe. After the cosmic microwave background was emitted, the universe entered a period when neutral hydrogen filled the intergalactic space. For the universe to become transparent to ultraviolet light again, large numbers of luminous objects needed to emit enough radiation to ionize that hydrogen. The timeline of reionization has been challenging to reconcile with the number of early stars expected from traditional models. Dark stars, with their large radii and long lives, could contribute significantly to reionization. Their diffuse but steady glow would emit radiation capable of ionizing gas over large distances. Even if dark stars were relatively rare, their large sizes and long lives could make them important contributors to this critical phase of cosmic evolution. Dark stars also offer insights into the distribution and behavior of dark matter halos. Because these stars require dense concentrations of dark matter to form, their presence would indicate that certain regions of the early universe had more tightly clustered dark matter than models anticipated. This, in turn, reveals something about how dark matter behaved shortly after the Big Bang. It suggests that dark matter may have clumped more efficiently or more rapidly than previously believed. Such information would help refine cosmological simulations, improving our understanding of how galaxies formed and how structure evolved across billions of years. In addition, the existence of dark stars would influence theories about how baryonic matter, ordinary matter, interacts with dark matter. While dark matter rarely interacts with normal matter directly, the processes that allow dark stars to form require a complex interplay between the two. Gas and dark matter must both fall into the same gravitational well. They must accumulate in such a way that annihilations occur without immediately dissipating the energy. This delicate balance would give researchers new constraints on how dark matter moves, how it distributes itself within halos, and how it behaves under the extreme conditions of the early universe. One of the most exciting implications of dark stars is the possibility that they could act as natural laboratories for studying physics beyond the standard model. These stars would operate in energy regimes and conditions impossible to replicate on Earth. Their behavior would provide indirect clues about the properties of dark matter particles, such as their masses, annihilation cross-sections, and potential interactions. By studying the light from dark stars, scientists could infer the characteristics of the particles powering them. This makes dark stars an extraordinary tool for connecting cosmic observations with fundamental physics. The implications extend beyond particle physics into the realm of cosmic structure formation. It would imply that the universe experimented with multiple pathways to producing light and structure. Instead of a single uniform process driving the formation of the first luminous objects, the early universe may have been a rich landscape filled with diverse types of stars and energy sources. This diversity might explain why some early galaxies appear unusual or why their properties deviate from standard predictions. It would highlight the creativity of cosmic processes during a period when conditions were extreme and rapidly evolving. Even the simple fact that dark stars could survive for long periods in the early universe, growing steadily without exploding, would alter the expected distribution of early light sources. Traditional models assumed that the first stars were short-lived and violent. Dark stars, with their gentle and persistent glow, would paint a calmer picture of cosmic dawn, one punctuated by immense but peaceful giants lighting up the darkness until their eventual collapse. These implications extend into the philosophical realm as well. Dark stars challenge our intuition about what a star is. They remind us that the universe can use entirely different mechanisms to achieve similar outcomes. A star does not need to rely on nuclear fusion to shine. Gravity and particle physics can create luminous bodies through entirely different pathways. This expands our understanding of what is possible in the cosmos. Ultimately, the implications of dark stars underscore the interconnectedness of cosmic phenomena. Dark matter physics influences star formation. Star formation influences black hole growth. Black hole growth influences galaxy evolution. Galaxy evolution influences the distribution of matter across the universe. Everything is connected, and the possibility of dark stars highlights just how deep those connections go. The idea that dark matter might have powered some of the earliest stars ties the invisible to the visible in a profound way. It suggests that the universe's darkness did not merely sit in the background shaping galaxies subtly, but may have played an active and luminous role in the cosmos's earliest chapters. The glow of dark stars, if it existed, would be the universe revealing its hidden structure in the most dramatic way imaginable.
The discoveries emerging from the James Webb Space Telescope mark a turning point in our understanding of the universe's earliest moments. Each compact bright source, each unexpected spectral feature, and each puzzling observation invites us to rethink the story of cosmic dawn. For generations, astronomers imagined the early universe as a place governed by familiar processes: gas collapsing into stars, stars clustering into galaxies, galaxies merging to form larger structures, and black holes growing slowly from the remnants of the first stellar explosions. That picture was simple, elegant, and mostly consistent with the limited evidence available at the time. But now, the universe is telling us that the truth may be far richer. Webb's observations have shown that the early cosmos may have contained objects so unusual that their existence was barely considered possible. It has revealed a landscape where the ordinary rules of star formation may have been accompanied by exotic pathways, where dark matter may have acted not only as an invisible gravitational scaffold, but as a luminous power source, and where the seeds of supermassive black holes may have been planted far earlier and far more efficiently than we ever imagined. We are now witnessing the first glimpses of a cosmic dawn that is more dynamic, more diverse, and more surprising than the models that preceded Webb ever anticipated. The future of this field will be shaped by how scientists respond to these discoveries. Already, teams around the world are preparing proposals for deeper Webb observations, targeting the most promising dark star candidates. These observations will aim to capture higher-resolution spectra, refine redshift measurements, and determine whether the faint helium absorption line and other predicted features are truly present. Webb has the sensitivity to provide definitive answers, but answering these questions will require more observing time, careful planning, and continued collaboration between observational astronomers and theorists. Beyond Webb, other telescopes will join the effort. Ground-based observatories equipped with adaptive optics will study these objects in complementary wavelengths, while instruments like the Atacama Large Millimeter/Sub-Millimeter Array will probe their surrounding environments, searching for gas signatures that distinguish stars from galaxies. The upcoming Nancy Grace Roman Space Telescope will survey wide areas of the sky, potentially identifying new high-redshift objects that resemble dark star candidates. The combination of deep observations from Webb and wide surveys from Roman will create a powerful dataset capable of testing theories of early cosmic evolution with unprecedented precision. As new data accumulate, theoretical models will evolve alongside them. Theorists will refine simulations of how dark stars form, grow, and collapse. They will explore new dark matter particle candidates that better match observed features. They will test hybrid models where dark matter heating and nuclear fusion coexist. And they will investigate how these exotic stars may have influenced the formation of early galaxies, the timing of reionization, and the growth of the first black holes. Each piece of evidence will be woven together into a more complete picture of the early universe, one that captures both the familiar and the unexpected. But the future of dark star research is not merely about collecting data or refining simulations. It is also about broadening our imagination. For decades, scientists assumed that stars in the early universe resembled the stars we see today, differing mostly in their mass and composition. The dark star hypothesis challenges that assumption profoundly. It suggests that the laws of physics allow for luminous objects that operate on entirely different principles, powered by processes invisible to the eye, yet fundamental to the cosmos. It reminds us that the universe is not obligated to follow patterns that are easy for humans to predict. There is a profound sense of humility embedded in this discovery. The cosmos is vast, and our understanding of it is still in its infancy. Each generation of astronomers builds upon the work of those who came before, using new tools to test old ideas. Webb represents one of the most powerful such tools humanity has created. It is showing us that even the assumptions we once considered solid may need to be revisited. The early universe may not have been a simple place governed by straightforward processes. It may have been a time of experimentation, where physical conditions allowed for the birth of objects that have not existed since. This recognition opens the door to new possibilities. If dark stars existed, what other exotic objects might the early universe have produced? Could there have been stars powered by entirely different mechanisms? Could dark matter interactions have shaped cosmic evolution in ways we have not yet imagined? These questions are not idle speculation. They are starting points for future research.
As new instruments come online and new models are developed, astronomers will explore these possibilities with increasing depth. The search for dark stars is also a search for the nature of dark matter itself. Understanding dark matter is one of the most pressing challenges in modern physics. Despite its profound influence on the structure of the universe, we still do not know what dark matter actually is. For decades, researchers have attempted to detect dark matter particles directly through laboratory experiments, but success has remained elusive. If dark stars are proven real, they will provide a different avenue for discovering the properties of dark matter, an astrophysical pathway rather than a laboratory one. The light of dark stars, captured across billions of years, could encode information about dark matter interactions that no experiment on Earth could ever replicate. This cosmic perspective underscores why the search for dark stars is more than a niche area of astronomy. It sits at the crossroads of multiple scientific disciplines. It connects particle physics, cosmology, astrophysics, and even philosophy. It raises questions about the nature of matter, the origins of structure, and the universe's capacity to surprise us. It shows us that the universe is a living laboratory filled with experiments conducted on scales far beyond anything humans can create. As we look toward the future, it is essential to remember that the search for dark stars is not driven merely by the desire to confirm a theory. It is driven by curiosity, the same force that has guided science for centuries. It is driven by the thrill of discovery, the joy of uncovering something unexpected, and the hope that each new answer reveals deeper layers of the cosmic story. It is driven by the understanding that the universe is far too vast to be fully understood by simple models alone. The James Webb Space Telescope has opened a window into the earliest chapters of cosmic history. Through that window, we see not only galaxies and stars, but mysteries that challenge the boundaries of what we thought possible. Whether dark stars ultimately prove to be real, or whether another surprising explanation emerges, the journey of exploration will reshape our understanding of the universe's origins. In this new era of discovery, humanity stands at the edge of a deeper understanding of the universe. The early universe is speaking to us through light that has traveled across billions of years, carrying with it the signatures of ancient structures and forgotten processes. As we decode those messages, we uncover not only scientific truths, but also something profoundly human, the sense of wonder that emerges when we confront the unknown. And that is the promise of the future. The mysteries revealed by Webb are not the end of the story. They are the beginning of a new chapter, one filled with questions, discoveries, and revelations that will reshape our understanding of the universe for generations to come. Please subscribe and like if you enjoyed this video. Hope to see you join us soon in another session from Wisdom Sleepers.